no, software updates. Okay, let's go ahead and get started. And I think I just realized, I think I posted this morning's lecture notes for you guys. Those are not yours. I'll delete that. I've only given myself 10 minutes in between these two. That's totally not enough time. So hopefully I won't start late very often, but sometimes I might. Okay. Oh my goodness. Let's go ahead and get started then. So, where did we leave off? We were talking about resonance, right? So, resonance again being such an important topic that we want to make sure that we really understand when things resonate. Whoops. Why some are going to be better than others as resonance contributors. Why structures are better than others. So I'm going to looking in the book, and I'm going to choose a couple of problems, and we're going to take a look at some resonance about these things. So, what do we have here? Is this an incorporated? Yes. Okay. So, first molecule here, we want to think about resonating. We have a couple places we can resonate from, right? So, looking at these, we're gonna say, okay, well, we have to start resonance from either a double bond or a lone pair. In this molecule, we have no double bonds, but we do have some lone pairs. So, we've got a couple things. We've got two kind of sites we can go for our lone pairs here. So, with our first one, let's go ahead and go from the oxygen. If we move that down, so that carbon with the positive charge on it has an incomplete octet, right? It's only got 6 electrons. That's why it has a positive charge on that carbon. If we do this, we're going to end up having this as our structure. And just for fun, we're going to call this one number 2. We'll call our original one number 1. And let's go ahead and see also if we are going to resonate from the nitrogen lone pair instead. Let's do that one in blue. So just starting from that lone pair, going down. If we do that, we're going to end up with this is so ugly. So I'm using a slightly different tablet because the other one is out of battery. This one is it's not as nice with its structures. Look at how ugly that is. Okay, hold on. Let me try this one more time. Let's try this one more time. Good enough. And this one will be number 3. So, if we are looking at all 3 of these, we have our original molecule, we have resonance form 2, and we have resonance form 3. Looking at those, let's talk about why some of them might be better than others. If we see here, really the difference is, let's see, we'll go back to black. The only difference in these molecules is is really where that positive charge is going. And so we have to think, okay, in molecule 1, it's on carbon. On molecule 2, it's on oxygen. In molecule 3, I'm sorry, these are not different molecules. They're the same molecule, but different resonance forms. In form 3, it's on nitrogen. So 1 is a positive carbon. Number 2 is a positive oxygen. And a 3 is a positive nitrogen. And so if we're trying to think which of these is going to be the best one, what are we thinking? What's our kind of rule for positive charges? I realize I've got a lone pair here. What's our rule for positive charges? Where do we want to put those? Back in blue, perhaps. Well, recall that the most stable positive charge is on the is going to be on the so yes, we do want so both of those are correct. We do want positives close to negative charges, and we do want them to be more substituted if that's on carbon. But before that, if we it's not even on this tablet, it's on the other one, but if you remember, kind of the first thing is we talked about, negative charges being on electronegative atoms first, and then from there we said, well, if it's got to be on carbon, then we're going to put it on the outside, right? We want it on a primary carbon if possible. With and then also, if all other things being equal, we'll put it as close to a positive as possible to kind of work it out. With positive charges, though, we had kind of the opposite trend, right? We saw that it's best to first put it on your least electronegative atom, and then from there, then you'll want it to be on a more substituted carbon if it's got to be on a carbon, and then from there, if it's got to be on a more substituted carbon closer to a negative charge, that's better. So it's really all three of those things, but hierarchically, the best thing to do is put it on your least electronegative atom first. And since the only difference with these, it's not really where it's placed, so we can't unfortunately just move our carbocation or our positive charge to more substituted or less substituted carbons in this. Just looking at the forms we have here, neither of those two statements are applicable for this particular set of molecules, since we don't have any negative charges, and all of our carbons in this case are secondary anyway, so we don't even have any more better places to put them. So, that in mind, what's the least electronegative atom of these three? Carbon, oxygen, or nitrogen? So remember, the more electronegative one is farther up and to the right, which is going to be oxygen, right? So oxygen is the most electronegative, followed by nitrogen, followed by carbon. So in terms of stability then, if we want it on the least electronegative atom, we're going to see that molecule 1, is going to be more stable than molecule 3, which is more stable than molecule 2. So this is most stable, and the one with the oxygen positive is going to be less stable. So if we were to rank these in terms of their stability, we'll say that resonance form 1 is the most stable because it's got its positive charge on the least electronegative atom. and then we're going to have it going forward. So our least stable has the positive on the most electronegative atom. So that's going to be that situation there. All right. Although we will find positive nitrogen is pretty common, we're still looking for carbon's going to kind of be a better option there. So, although, let's not get into it. Technically, the carbon's going to have an incomplete octet and the nitrogen doesn't, so nitrogen might be a little bit better in this case, but let's just worry about electronegativity right now. We're not going to go ahead and throw extra stuff at you right then. All right, let's do another one. So that's the problem with OChem, right? Is there's not with Gen Chem it's super easy. We calculate a number and poof, there we have it. But with stuff like this, you know, these might be equivalently stable to each other, but for sure the one with the oxygen is less stable, right? So let's look at another one. How about this one? We have a double bond there. Ugh, this pen's awful. Okay. My structures are so ugly. Okay. Couple places to resonate here. So we again can start from a lone pair or a double bond. Can do either one. We can go ahead and do that. If we just move this double bond over, I should make that more clear that it's going to become another double bond. If we do that, resonance arrow here. If we go ahead and draw this molecule, we now have our double bond here. We now have our positive charge here. Is this one going to be better or worse than it was before? This is worse, right? Because we've moved our carbocation from a tertiary position to now a secondary position. So we already know between molecules 1 and 2, 1 is more stable than 2 because we have a carbocation on a tertiary versus a secondary carbon. So, by the way, were we all able to see that the YouTube video on hyperconjugation? Just that kind of like there's just like really a 20-second segment of it that's useful, where you can actually see the orbitals overlapping and rotating around. Very hard to do in 2 dimensions, let alone with motion. So the video does have things moving around. Oh God, I'm yellow again. Magic light, come back and make me. Isn't that remarkable? I'm no longer yellow. I don't understand this. Oh, and I'm yellow again. Oh, well. Well, whatever. Okay, so that was option or our first kind of resonance there. We could also say, okay, I'm going to actually start on this lone pair of oxygen. And then we're going to keep on pushing our electrons over because we can't stop there. We can't stop next to the oxygen because then that carbon is going to have 5 bonds. So we keep on resonating. If we do that, we end up with this molecule. Ugh. I'm going to drive myself nuts with these structures. Okay, well, I'm sorry, today they're going to just be extra ugly. I'll try to use this tablet for Gen Chem so I can save the power on the other one, and I'll also try to remember to charge the other one. It's a little bit easier to read, in my opinion. But anyways, looking at this, probably also is going to be not so great, right? So I'd say for this one, we're looking at, yeah, it's even less stable, right? So, because now we've got our positive charge on the oxygen. The oxygen is not going to be very happy at all. Probably the least stable of all. Oops. I would say that this one is now moving to even less stable. Probably least stable. So, again, our original molecule was the better one. That's going to be the major form of that molecule. Though these others will play a small effect as well. So again, with resonance, it's never just one thing we're looking at. We're looking at multiples. Okay. Cool. Let's look at another example here. Or not, I mean, not an example. So that's kind of resonance for us. We'll talk about resonance in the next chapter too, so I'm not terribly worried about doing more practice right now. But if we're to understand resonance a little bit more, let's look at a couple of molecules. So, okay, let's try this again. There we go. This molecule, by the way, called pyridine. It's important to note that we'll sometimes have a distinction between what's called a localized electron pair and a delocalized electron pair. If we have instead this molecule, say we've got this. Actually, this is not a great example either. Where shall we put this? Let's just look at it right now. Just one molecule. If we're looking at this pyridine, it's important for us to understand when a lone pair can kind of mess with things or not. If we take a look at this molecule's orbitals, which I'm terrible at drawing, but here we go. Let's try it out. I'm gonna try and like paste it and then rotate it maybe. Can I do that? Rotate. Oh, I can't rotate it. Oh darn. Okay, I'm gonna have to try again. Okay, I'm gonna redraw it so I can draw the orb. Actually, I can probably mess with this enough. Whatever, we're gonna try it out. Okay, orbitals. Let's draw some. What color shall we do? Blue, yes. Okay. We have our p orbitals here participating in these double bonds, right? And here's our other p orbital. So, if we're looking at this, that nitrogen has got the p orbital sticking straight up, but these electrons are still in an sp2 orbital. Come in, come on. You're always scratching at the door to be let in. Yes, hi. You want to come up here? You want to say hi to everybody? Okay. So those p orbitals that are participating in the double bonds here, the resonance can only happen in those blue orbitals. So the resonance is happening within the p orbitals only. So those molecules which have their one electron in them, or those atoms, they have one electron in those p orbitals that are forming double bonds with each other by overlapping, right? And we saw that the resonance means they can kind of decide which way to go. They can go to the right or to the left, and they can bond with different things, right? That lone pair in nitrogen, though, is actually kind of chilling in an sp2 orbital. So it has the p electrons that are contributing to the double bond on its left, but those that lone pair of electrons, it's actually pointing, it's in the same plane as the rest of the molecule. So remember, sp2 is planar, so all of those are planar little bits there, and so that lone pair is actually sticking out, in the same plane as the rest of the molecule. So those electrons are effectively, let me do it in purple because that's what I did just a second ago. Those sp2 electrons are not able to participate. Oh, I'm out of room. Participate. Okay, Miss Jersey, you're going to go on to your little bed. Because geometrically they are removed from the pi system. So all those pi orbitals that we can resonate with, those are all pointing up and down. Now she wants to go out. Go figure. So those p orbitals are sticking up and down. Imagine this is our flat pyridine. All those p orbitals are sticking up and down. The lone pair on the nitrogen is sticking kind of straight out. So it's not able to really participate. They're removed. There's not part of that system. And so those aren't going to participate. We call this is called a so this is a localized pair. Meaning they're stuck in one spot. They're not going to move about with the resonance. All right, so those electrons are stuck in one little spot. All right, so it just depends on the hybridization there, right? If, however, we had something like this, very important structure here. This is the pentadiene anion, cyclopentadiene. We're going to see that this lone pair, what do you mean by impact? So the p orbitals are filled, right? So we've got, with this nitrogen, we have one electron in one sp2 orbital going to the right. We have one electron in an sp2 orbital going left. We have one electron in the pi orbital, that is a p orbital, that is forming a pi bond, also to the left. And then we have the remaining lone pair in an sp2 orbital pointing away from the rest of the molecule. So those electrons are not able to, because they're not in a p orbital, they don't have access to a p orbital, they're not in the same geometry, they're 90 degrees away from everything else. There's just not the overlap necessary to kind of allow them to. So because they're 90 degrees apart, p orbital straight up, sp2 orbital going outside, with all the other p orbitals around this molecule that are also straight up and down, this one that's pointing out to the side is not going to be able to interact there. So hopefully that answers that question. But if we take a look at this one, I think it'll be even more clear. So note that this is this carbon here is sp3, right? So that means that there are indeed orbitals that are geometrically similar. Remember, with sp3 carbons, we have 4 orbitals. One of them is pointing up, 3 of them are pointing down in various angles, right? With sp2, we have everything in the same plane, and then we have one thing up and down, right? So with these, we can see that, okay, well, that lobe that's pointing up in the sp3 is pointing in the same direction as a p orbital of an sp2 hybridized carbon. And so, if we try and draw these lobes here, here's our... Those are all our p orbitals. But on that other one, we actually have an sp3 orbital that's still pointing up, or it can point up. And, you know, these things are, it's pointing up, we'll say. Even if it's pointing down, it doesn't matter because there's p orbitals on the bottom side too. So either way. And if we've got this kind of sp3 orbital here, we can see that, in fact, now these are in the same geometry as all of those p orbitals. And as a result, that lone pair is free to participate. So this lone pair can say, okay, now I'm going here, and you go here. Actually, I'm gonna switch colors again, because I'll be consistent with that. I think I use light blue. And lo and behold, look what happens now. All we've done, is much like the benzene. We now have our double bonds here, and look, now there's our negative charge. And so it's really just kind of moved around. And so it was on, let's call it carbon 1 before, even though that's not what we'll number that in real life when we talk about naming these things. It's now on carbon 2 instead, that lone pair. And it can go wherever it wants. Instead of pushing these electrons, I could have said, okay, you know what, I'm going to just... I'm going to decide to now dump this one on that carbon. And if I do that, totally okay. I can say now I get... Now I've got my lone pair here. And so we can just kind of move this lone pair around. As a result, we call this one, that's a negative charge as well, this is a delocalized lone pair. It's able to move around, essentially. So delocalized, not stuck in one location, it's able to move around. So that lone pair is delocalized because it's in an orbital that is pointing in the same direction as the p orbitals that are available to us for resonating. Whereas with the pyridine, previously that one was pointing perpendicularly to the orbitals. There was not any overlap there that we could have. And so as a result of that, we're not going to be able to add that into the system. And indeed, if you were to try and resonate off that the lone pair there, you would not be able to make anything better anyway. So even if you tried resonating with that, it would just make things a lot worse. So you don't have to worry about that. So suffice it to say, anytime you have an sp3 hybridized lone pair, so a lone pair that's on an atom that is sp3 hybridized, those ones you should be able to resonate with other double bonds. If it's going to be on an sp2 or sp, you're not going to be able to resonate it. So that's kind of our distinction there. All right, and so, but in terms of what we will call those lone pair, we have localized ones, which are stuck. They cannot participate in resonance. And then we have localized ones. So there we have that. All right, do we have questions on that little bit there? All right, let's do some. Let's start talking about acids and bases, because we're going to talk a lot about resonance here too. So, if there's no questions on that, I'm going to go ahead and start talking about acids and bases. In organic molecules. And we're going to see we have a number of different factors that are going to make certain things better at being acids and certain things worse. All right, and so if we are going to start talking about this, we just want to have kind of an idea in mind of relative strengths of acids before we even talk about the properties that make things more acidic or less acidic. Let's just start with a couple of examples. Typically, if you're looking at a strong acid like hydrochloric acid or hydrobromic acid, the pKa of that is going to be, it'll be less than 0, right? Those typically have negative pKa's because they fully dissociate. We saw those are strong acids. Let's just say HCl, because I don't want to say HX because that could potentially include fluorine, and that's not one that would apply. We're going to see that there are other things that will also have pKa's below 0. We're going to see, and I'm going to put our acidic H's in blue. When we're looking at these hydrogens, remember, mostly we're going to be talking about Bronsted-Lowry acids and bases. Those are going to be ones that are proton donors or proton acceptors, respectively. All three of these are going to have pKa's that are below 0. So if you have a protonated oxygen, meaning you've added a proton to it, it's going to be quite acidic. So H3O plus, hydronium, acidic. This protonated ketone. Oh, we still haven't talked about functional groups, have we? Blah. Okay. Okay. See, this book, we do functional groups differently. Normally I teach them during spectroscopy, but apparently we do it a little bit earlier in this book. So we got to hold off on acid-base just for a second here. We'll continue on with this in just a little bit. I'm going to move this down because we have to talk about functional groups really quickly so that we're not missing that bit here. Okay, I'm just going to cut this. We'll talk about it later. So sorry, I forgot we have to talk about functional groups really quickly. So I did give you that chart of different functional groups. These are going to be the things that are going to be classes of reaction that we have. We're going to see that, typically if we expose the same functional group to the same conditions, whatever else is on the molecule, it's going to react the same way, by and large. So some functional groups that we're going to talk about are first alkanes. These are just hydrocarbons. These first couple are just hydrocarbons. These are going to have single bonds only. We're going to have alkenes, which have double bonds involved. I'm going to put R's on these. R's can either be not ralcanes and ralkenes, but R can be more carbons or more hydrogens, either way. If we have a triple bond, those are called alkynes. We'll be talking about all of these this semester, so all of these hydrocarbons. They just, we're looking at these double, triple, and single bonds here for these three functional groups. We're going to see we have aromatics, like benzene. We're going to talk about aromatic compounds next semester, but those are going to be things that have benzenes or something similar. That cyclopentadiene that had the lone pair that was delocalized above, as well as the period, those are both aromatic compounds, but we'll see that later on. If you have an OH bound to a carbon, that's called an alcohol. If you have an oxygen sandwiched in between carbons, that's called an ether. So just remember, R is hydrogen or some other carbon. Could be more carbon chains, whatever, some other carbon there. So for all of these. All right, we can also have things with oxygens that have double bonds. This is called an aldehyde. An aldehyde has a carbonyl. C double bond O, remember, is called a carbonyl. And they also have a hydrogen attached to that carbonyl. So the rest of the molecule, whatever the R is, something else, this C double bond O with the H is called an aldehyde. R could be H. You could have formaldehyde, which is just another H there. If you have a carbonyl that is sandwiched between two other carbons, that's called a ketone. So that carbonyl has got a carbon on each side and then other stuff. That's called a ketone. Actually, this can be R right here. This is called an ester, where you have a carbonyl and an ether essentially at once. So you have a carbon double bonded to O and single bonded to O, and then you have another carbon on the other side of the other oxygen. So that's called an ester. If you have an OH on that carbon that has a carbonyl, that's called a carboxylic acid. So you have carbon double bonded to oxygen as well as single bonded to OH. So this time it's a ketone or an aldehyde, a carbonyl and a alcohol at the same time. That's called a carboxylic acid. And then what else do we have? Let's see, is that enough of oxygen? I think so. That's all the oxygen ones, yeah. If we have some nitrogen in there, just nitrogen with various carbons. That's called an amine. If you have so remember, nitrogen makes two bonds, that's why we have R2 on it. So again, could be H, could be other ones. Yes, this is an amide. Pronounced amide. So even though it's so nice to say amide, it is technically pronounced amide. Yes, very good. Is that it for nitrogen? I mean, did we talk about imides? This is technically called an imide. These are less common. We're not going to see these as often, but they exist. Those are imides. And I think that's it for nitrogen. No, we have nitrile. Sorry. So a C triple bonded to N. That's a nitrile. Yep. So in chemistry, it's pronounced amide. So even though it's so nice to say like formamide, it's technically formamide. So drives me nuts too. I remember for the longest time I didn't even pronounce it carbonyl. I was like carbonyl, and then I got yelled at a lot for that. But anyways, that's okay. How about sulfur? This is a thiol. This is a sulfide. Sulfur, again, we're going to see, we don't really talk about this semester anyway, so what other, am I forgetting anything? That's pretty good, honestly. Mostly it's oxygen and nitrogen, so that's enough for functional groups. So we're going to see a lot of these we're going to focus on this semester are going to be these three right here, the alkenes, alkynes, and alcohols. That's what we're covering this semester. We're also going to talk about alkyl halides. I'll put that as well. So that would be like methyl bromide or whatever. Those are alkyl halides. So it's something carbon with a halogen. So X equals one of our halogens here. All right, so those are alkyl halides. I guess that needs to be a carbon, so I'm going to put that carbon there. There. So now we have a carbon. So those are alkyl halides. And those we'll also talk about this semester. So with all those in mind, now let's talk about acids and bases. So those you'll just want to learn, these are patterns. When you see atoms arranged in these ways, we're going to see they're going to behave similarly to each other. So no matter what ester you have, so say you've got this ester versus, I need an oxygen there. Whatever. These two are both esters. And we're going to see all those other carbons there don't really matter. Our esters are going to behave the same way as each other. So when we talk about esters as a functional group, which will be next semester, we'll see all the things we can do with esters. And it's really anything that has this same pattern here. So we have the C double bond O as well as the kind of that ether part together. Those are going to behave similarly to each other. So if we submit both of these molecules to the same conditions, the same thing is going to happen to both of them. And so, you know, for example, if we give them some acidic conditions, a little bit of heat, we're going to end up, and we'll even put some water in there. if we just go ahead, this is just not something you need to know right now, but for example, we're going to see that both of those are going to essentially just break apart, and we're going to end up getting similar products out. So you see what's happened in this particular thing, just an example. But what we see is we've essentially kind of cleaved these molecules in half, turned one into a carboxylic acid and the other into an alcohol. And so we're going to see that despite these being very different molecules in terms of like a, molecular structure and everything, that functional group there is where the chemistry is taking place, and they're going to react the same way, producing very similar molecules. So they've both produced a carboxylic acid and an alcohol as we hydrolyzed them. So that aside, that's just an example of the point of functional groups. So, okay, we're done. I'll stop talking about that. Okay, so that was just an example. So that's the purpose of learning these functional groups, is because they behave similarly. Oh, here we go, back to acids and bases. Sorry, I forgot I have to cover functional groups earlier in this book. So, okay. So, these guys have pKa's below 0. They're very acidic, right? So, these things are very happy to get rid of their protons. We're going to see that carboxylic acids, these guys have pKa's of around 5 or so. So I'm just going to give you some pKa's in general just so we have a ballpark idea of how acidic things are. Remember, a pKa unit is a power of 10. So this carboxylic acid, compared to one of these original ones, is at least 100,000 times less acidic than those three molecules above. So remember, these are powers of 10. So 10 to the 5 times less acidic with a higher pKa. All right. Let's see, what else do we have? We've got phenols. Those are aromatic alcohols, as well as diketones. I'm sorry, I need to put my H's in blue so we're very clear about what blue or what H we're talking about. These both have pKa's of roughly 10 or so, so another 100,000 times less acidic than the previous one. We're going to see that alcohols and water, those have pKa's around 15 or so. And then if we start looking at, what are we looking at for 20? Not much around 20. Maybe we're looking at, I'm sorry, once again I have not put one of our H's in blue. This will probably be around 20. We're going to talk about why these are like that, but we're going to see again, we're starting at most acidic, we're going to less and less acidic. Blue. This one, this alkyne, triple bonded carbon, we're looking at about 25 or so. Amines, we're looking at about 35. Remember, high pKa means less acidic. 35 to 40. So these are, there's a range. So not acidic. That's the point. So consider water pKa of 15 versus a pKa of 35. Like, water is way more acidic than these other things. And so if you think about water, pure water, we don't even really consider that acidic, right? It can act as an acid, but it's so the amount of ionization there is so small. Just with these other ones, it's completely non-existent. You're going to need some super strong bases to work with these, to get these to deprotonate. If we go now to alkenes, those we're looking at about 45 or so. And then finally, just a plain old normal carbon CH bond. That's about 50. So a CH bond is very unlikely to be broken, as is. So a normal sp3 hybridized carbon hydrogen bond, very strong bond. We're not going to be breaking that very easily. All right, but again here we're seeing there's a huge array of various kind of categories we're going to have here. And we're going to see why these are the case. So let's look at those first examples. We saw water, pKa of about 15 or so, but if we protonate it, now it has a pKa that's less than 0, so it's extremely acidic once we've protonated it. So, and we're going to see that it's going to be about the same for protonated alcohols as well. So if we protonate an alcohol, we're looking at something about the pKa of less than 0. And so that's going to be our kind of first category of things. So these, I'm not going to give you in any particular order of categories. It's not really fair to do an apples to oranges comparison. So with all these, I'm going to try and give you apples to apples. So we're going to see here ways of talking about this. So if I have, for example, ethanol, protonated ethanol, and then ethoxide, we're going to see if we just kind of look above, if we're just comparing these, why do we think the middle one is so much more acidic than the left one? We're not even going to talk about the right one, because the right one's not an acid at all. There's not even a hydrogen on that oxygen. I mean, sure, you've got the CHs nearby, but again, that's like 50 or so. So not even an acid. Why do we see that that cationic version, the protonated form, is more acidic? Why? The reason for this, and I'm going to say this 200 times, indeed it has more hydrogens, but let's look at it another way. Acid strength is proportional to the stability of the conjugate base. So the conjugate base is what remains after it gives away its proton. So ignoring this last one here, if we look at these, let's look at these two. So we have our alcohol, plain old alcohol. If we put a base in, we are left with this, right? So we had two lone pairs, neutral oxygen. We now have a negatively charged oxygen there. If we start with our cationic form and we remove a proton, we end up with this. So these are our conjugate bases here. So if we're looking at these conjugate bases, hopefully we can see one of them is obviously more stable than the other, right? We know that stable things do not have formal charges, right? Formal charges are bad. They make things unstable. Sometimes they're unavoidable, though, of course. And so we're going to see clearly this one is more stable than the other one. Versus that negatively charged one above it. We all see that, yes? In terms of these conjugate bases, the two molecules on the right, we see that our alkoxide, as we call it, the negatively charged one has a formal charge. The one below it does not have a formal charge. And so as a result, the one below it's going to be more stable. If the conjugate base is more stable, that means our starting material is more likely to form that conjugate base. The more stable your conjugate base is, the less stable your acid is. And, as we perhaps remember, less stable is the same thing as saying more acidic. So more likely to react, right? More reactive. It wants to become stable, yes? In fact, that top one is becoming less stable over the course of the reaction. If that ethanol loses its proton, it's now negatively charged, is less stable than it was before. However, if this, I don't even know what to call it, this ethanol that's protonated loses a proton, it becomes ethanol, neutral, stable. So as a result, we see that this protonated form is a stronger acid than the regular neutral form. And, I mean, if that other one had another hydrogen to lose, even though it doesn't, obviously it's not going to make anything more stable, right? You can't even lose a hydrogen there. If we lose a hydrogen, we now have a negatively charged carbon and a negatively charged oxygen in the same molecule, extremely unstable. It's not going to happen. So that's the difference here. So the point of this little section is, the takeaway here, is that cationic acids are stronger than neutral ones. Because, as we're going to see for all of these cases, their conjugate bases are more stable. Therefore, the acid is stronger if your conjugate base is more stable. That's the core lesson here. We're going to look at all of these categories of acids and see why their particular conjugate base is more or less stable, and we're going to compare them. Is this okay, the cationic acid category? If we're looking at these two, ammonia versus ammonium, hopefully we can see that the ammonium is going to be the acidic one, the more acidic compound between the two. Because if we take away one hydrogen from each molecule, we end up with ammonia from the top case, and we end up with, this time it's an amide. NH2 minus is amide, pronounced that way. Isn't that nice? But let's not worry about that. But that if we make it negative, that's less stable than just making it neutral, right? So we're going to see that cationic acids are going to be more acidic than their neutral counterparts. All right, perhaps the most obvious of all of the categories we're going to talk about here. All right. We probably have time for one more. Let's take a look at something like this. If I were to tell you the pKa, if this is about 10, pKa is about 15, what's the only difference between these molecules? Well, one's an oxygen, one's a sulfur, right? So that's the only difference. Then let's try and figure out why the sulfur one is more acidic than the oxygen-based one. And so, if we go ahead and take a look at that, let's look at their conjugate bases. They both have a negative charge, so no difference there. But let's think about these in terms of their characteristics as atoms. What's the main difference between sulfur and oxygen? Physically speaking. We know that oxygen is more electronegative than sulfur is, right? So we might be like, well, oxygen is going to be happy with the negative charge, right? It's electronegative. That's a fair point, but there's something more important here. The main difference between oxygen and sulfur for this purpose is that sulfur, we'll do it this way. Here's our oxygen. And here's our sulfur. With keeping in mind that the sulfur is much, much bigger than oxygen is. Sulfur is in period 3, oxygen is in period 2. Sulfur has a whole set of d orbitals that it can deal with. It's got a much bigger atom than oxygen does. And so we're going to see that if you have a negative charge in this thing versus a negative charge in that thing, in terms of concentration, if we think back to our solution chemistry, which one of these is going to be more concentrated in terms of negative charge? Let's say we have the -1 charge and the volume of our atom. We're going to see, because the sulfur is so much bigger, is that with the sulfur, we're going to have a less concentrated charge. And so, if we think about the oxygen versus the sulfur, the oxygen has smaller orbitals. Those orbitals are closer to each other. They're closer to the nucleus. They're closer to each other. We're more likely to have, unfavorable kind of bonking in between the oxygen's lone pairs and the sulfur's lone pairs. The oxygen lone pairs are closer closer to each other, they're more concentrated, more of them in a smaller volume, they're more likely to bonk into each other, which is not likely. They repel each other, right? So this is a little bit less stable. In the sulfur, your orbitals are farther apart, and so they're less likely to bump into each other. Remember, they do repel each other, so there's less kind of repulsion happening here. Because the orbitals are farther apart. And so as a result, sulfur is better to accommodate that negative charge than oxygen is. And so we have a word for this. We call this polarizability. Polarizability. And so this essentially means the capacity of an atom to accommodate a charge. So, sulfur being bigger is able to accommodate that extra one. Well, if we're looking at it, the sulfur has a pK of 10 versus the oxygen version with a pK of 15. So we're looking at a difference of 100,000. So the sulfur there is 100,000 times more acidic than the oxygen one. So the pKs should be different. Let's see if we can find out the exact numbers. That'll be interesting. Let's see if I'm just completely lying to you or not. So ethanol, let's see its pKa. It's 15.9. Okay, and then the pKa of, so pKa is 15.9 if we were to look it up. For this molecule, for the same molecule with the sulfur, we're looking at 9.64. So again, still roughly, this time it's 1,000,000 times more acidic, but 1,000,000 versus 100,000, pretty close. So the reason that the sulfur is so much stronger as an acid, even though it looks exactly the same, the only difference is that one atom. The fact that the sulfur is bigger, it can accommodate a negative charge more easily. And so as a result, it's going to be much, much more acidic than the equivalent oxygen-containing compound. Does that kind of address that question? So I wouldn't say these are similar pKs. A difference of 1,000,000. Similar pKs, I would say, 10 versus 10.5. Like, that would be similar. But anything where you have more than an order of magnitude in between them, I would say it's significant. So, polarizability, let me just finish this thought. This trend increases, polarizability increases with atomic size. So we're going to see, cool. That we're going to see kind of our iodine there is kind of the most polarizable of our kind of common elements we see in organic chemistry. So that's why we're looking at this. So we're going to see that it increases as we go down the periodic table, as we go through there. All right, and so again, there's not any particular hard and fast, polarizability always wins. Sure, it really is only going to be applicable if we're going down the periodic table. While it is true that as you go left on the periodic table, things get bigger, they're not really getting that much bigger as we go left. So the difference between oxygen and nitrogen is very small in terms of atomic size, right? very small difference between those. But oxygen versus sulfur, huge difference. So we're going to see that polarizability, really, we're only going to see a downward trend. So we're not going to worry about a left-right trend here, because the differences in atomic size are not very big. And in fact, we see that electronegativity is going to kind of take over for that. So polarizability comes into play when we're looking in the same group. So, oh, I don't want to use that too bright. So you're going to look at polarizability when comparing elements in a group. If they're not in the same group, we're going to look at electronegativity instead. When you're comparing elements in a period. So we saw, for example, an acid containing sulfur is more acidic than the same acid containing oxygen. But we're going to see that oxygen containing one is going to be better than the nitrogen one. Oxygen, the alcohol, pKa 15, amine, pKa 35. So 10 to the 20th power times more acidic. So this is due to electronegativity. This is due to polarizability. So farther down you go in a group, the more acidic your acid will be. And then otherwise, if you're just comparing elements within the same period, you're looking at electronegativity. So you're looking at the one farther to the right. So notice again, HF, same period as oxygen, is going to have a much more acidic hydrogen, right? pKa of like 3 or so, versus the 15 of this. So this is also electronegativity because those are in the same, these are the same period. But this is the same group. So remember, group vertical on the periodic table, period same row. So I'm not gonna, I mean, I can put both of these together. I could say nitrogen versus sulfur, what's better? Should be obvious that it's sulfur because it's not only to the right, but it's also down. So it's both of those. But I'm not going to ask you, say, phosphorus versus oxygen. That's not a fair comparison. So stuff that goes down is good. Well, that's why we're going to see, actually, that's why HI is our strongest acid in terms of just things attached to one element. We're going to see that that's going to be our strongest acid, and it's also the most polarizable. So it's very far down to the right. That's going to be our most strong acid. As we go, CH, super weak acid, incredibly weak, 10 to the 50, right? Or negative 50, I guess, would be for the amount of stuff breaking apart. So we'll continue with this on. So even though Monday is a holiday, I think I'm still gonna go ahead and record for you guys, because we missed that first day due to the flights and stuff being a pain. So we'll continue this, and yeah, we'll go from there. So we have a couple more categories of acids here. We'll continue with this identity of the atom that the hydrogen is attached to on Monday. Again, you can just watch that later. Watch it on Tuesday. You can enjoy your holiday. And so we'll go from there. Alrighty. Any questions before we end for the day? Let me just go ahead and take a look at your homework. Let's see if we have enough to do it now. No, we have resonance here. You still can't do 12 and 13. So homework is still not due. So we'll see. Maybe it'll be due next Monday, as in 12 days from now, before your first homework is due. It's ridiculous. Over the weekend, I'll probably also put up your first couple of labs, so you can start with those. Those will be due, a couple of weeks after I post them, so you'll have time to work on those as well. Okay. Anything? Looks like no questions so far, so great. I will, in that case, see you all on Monday, maybe, if you feel like it. Otherwise, I'll see you Wednesday. So, but there will be a video probably up Monday afternoon. So, if you want to watch it then or Tuesday, go ahead. So, all right, cool. See you later. Enjoy your weekend.